Hello, welcome to the course SJPHY1B01 Mechanics 1. The contents of this course is taken from an Introduction to Mechanics by Klepner and Kolenko. We'll continue to discuss topics from Chapter 4, Work and Energy. In the last class, I have introduced the concept of potential energy, and we have seen for certain force field like conservative force, gravitational force, or the linear harmonic force, how to calculate the potential energy. So in reality, we are not calculating the actual value of the potential, we are calculating the potential difference. Okay, so if you have a particle which moves from initial point A to final point B, then the difference in potential energy between these 2 points, UB minus UA, is given as minus integral A to B F dot dr. So this is it's the amount of work done to move the particle from A to B against the force field. Okay. Now, what all information we can get from this potential energy expression, or what does the potential energy exactly tell us about the force which is acting on the system? Many a time it is easier to characterize a force by giving its potential energy function rather than specifying each of its components. In such cases, we would like to use our knowledge of the potential energy to determine what the force is acting. In other words, if you know the potential energy, you can calculate the corresponding force. Let's now try to see what is the exact relation between potential energy and force. For simplicity, let's take the case of a one-dimensional system like a mass spring system. So here f of x is the force acting along the x direction, and when you rewrite this expression into one-dimensional, you have ub minus ua equal to negative integral xa to xb f of x dx. Now let's assume that the particle moves from initial point x to a final point x plus delta x. So A is x and B is x plus delta x. For this motion, I can write delta U, the change in potential energy, as U of x plus delta x minus U of x, which is equal to integral x to x plus delta x f of x dx. Now let's invoke a trick which we use in most of our derivation. For sufficiently small delta x, I can assume that the force is constant over the range of integration. So in that way, I can take f of x outside this integral. Now integral of dx is x, you apply the limits, so you have minus f of x into x plus delta x minus x, which is minus f of x into delta x. Or f of x equal to minus delta u divided by delta x. In the limiting case, delta x tends to 0, you can replace this with a derivative. So you have the relation between force and potential energy as f of x equal to minus du by dx. Force is the negative derivative of the potential energy. So this is for one-dimensional case. In the three-dimensional case, this single derivative is replaced by the del operator, which is nothing but the derivative in all the three directions. So del operator is nothing but dou by dou x I cap plus dou by dou y j cap plus dou by dou z k cap. So in 3D you can write f of r equal to minus grad u or minus del u. So in essence, force is the negative derivative of the potential energy, or potential energy is the negative integral of the force. So once you know potential energy, you can calculate the corresponding force. So many a time in equations, instead of force, you use the potential energy term. One of the examples is the Schrödinger wave equation, which we use in quantum mechanics. So this is analogous to the equation of motion which we write in classical mechanics. As you know, in equation of motion you have the force term, but in Schrödinger equation you have the potential energy term. Because we know that from potential energy you can calculate the corresponding force. So it does the same job as the force in the classical equation of motion. Same way in condensed matter physics or solid state physics also, many of the time in equations you use the potential energy term. So you know that in materials, especially in crystalline materials, there is a regular periodic arrangement of atoms, which you call as lattice. And there are a lot of interaction between the atoms or the constituent particles in a lattice, right? A lot of force terms there. So it's practically impossible to measure all these forces or take them into account when you write an equation. So instead of what you do, you write the lattice potential energy function, which in a way encompasses all the force terms. So in some cases, it is much more convenient and physically meaningful to represent force in terms of its corresponding potential energy rather than its own components. Now, one of the advantages or one of the practical utilities of potential energy is that it not only helps you to compute the force acting on a system, it also allows you to understand the stability of the system under study. I can illustrate this with a simple example. Let's take the case of a one-dimensional harmonic oscillator. In the previous class, we have seen the general expression for the potential energy of a harmonic oscillator or a linear harmonic force. We have seen U of r equal to half kr minus r naught square, where r naught is the equilibrium position, r is the displacement from the equilibrium position, and k is the force constant. Okay. Now let's rewrite this into the one-dimensional case. So I have only one coordinate x. So u of x equal to half kx minus x naught square. Now if I choose my coordinate system in such a way that the equilibrium position corresponds to 0, then x naught equal to 0 now. So now my expression becomes u of x equal to half kx squared. So this is the potential energy function for a one-dimensional harmonic oscillator. Let's plot this so that we can get some important information graphically. So on the y-axis you have u of x, and on the x-axis you have x. So this is nothing but x square multiplied by a constant. You know that this kind of a second order function will give you a parabola. Okay, so this is the potential energy function. Now let's choose 3 points A, B and C. And let's try to analyze the potential energy and the corresponding force at these points. So at A, we know that the slope du by dx is positive, right? Slope is positive, du by dx is greater than 0. And force is nothing but a negative derivative of the potential minus du by dx. So since du by dx is positive here, the corresponding force is negative, which means if you have a particle at any of this position, then the force will act in such a way that it tends to move the particle in the minus x direction, in the opposite direction. Same way at point B, here you can see that the slope is negative, du by dx is less than 0. Consequently, the force is positive. So if you have a particle in the minus x direction, then the force will act in such a way that it tends to move the particle in the plus x direction, in the opposite direction. And at C, this is the minimum point. We know that at the minimum of a graph, the slope is 0. So du by dx is 0. Consequently, the force is also 0. So there is no force acts on the particle at this point. And that's why this is the equilibrium position. So if you do not apply any force on a spring mass system, or if you do not apply any force on a simple pendulum, this is the position the object is going to occupy, because this is the equilibrium position. Okay. Now, if you look at the force, we know that this is the restoring force, which means the force is always directed towards the origin, no matter which way the particle is displaced. The force vanishes only when the particle is at the origin. And from the potential energy graph, you can note that the minimum of the potential energy curve coincides with the equilibrium position of the system, right? Equilibrium position is x equal to 0, and we have seen that for this case, x naught equal to 0. Your equilibrium position is at 0. Right? So always in this kind of system, at the equilibrium position, your potential energy is going to be minimum. And this kind of an equilibrium point is known as a stable equilibrium point. And what's the meaning of stable equilibrium? If you try to move your particle away from this equilibrium, the system will work in such a way that it will bring the system back to this same equilibrium position. That's why it's known as a stable equilibrium. For example, if you try to displace your object slightly towards the right. Okay. So in the right, we know that the force is a negative force which tries to move your particle in the opposite direction. So what happens? The force will act in such a way that the object will be brought back to the same equilibrium position. On the other hand, if you displace the object slightly towards the left, we know that in the left side the force is positive, so it will act in such a way that the object will be brought back to the equilibrium position. So that's why we call this as a stable equilibrium position. So at this point the object can stay forever, right? So if you take a simple pendulum, if you do not apply any force, the bob will be at this equilibrium position till infinity, right? So this is a stable equilibrium. Now, are all the equilibrium points stable? That's the next question. So we know that for a point to be an equilibrium point, du by dx at that point has to be 0. Now let's take another potential energy function, just the opposite of previous case. So in the previous case you have a minima. Now let's take the opposite, you have a maxima here. So we know that from graph theory, at a maxima point as well as a minima point, the derivative or the slope is going to be 0. So if you calculate du by dx at this maximum point, once again you get 0. Now the question, is it an equilibrium position? So what do? You slightly displace it towards the right. So in the right you can see that u is decreasing, x is increasing, so du by dx is negative. And what is force? Negative of du by dx. So your force is going to be positive. And what's the meaning of positive force? If you make a displacement in the positive x direction, then the positive force will work in such a way that it tends to increase the displacement. So basically your particle is going to move further away from the equilibrium position. Same way, if you displace it slightly towards the left, what happens? Here u is decreasing, x is also decreasing, so du by dx is positive, consequently force is negative. And what's the meaning of a negative force? If you make a negative displacement, a displacement in the minus x direction, then the negative force will work in such a way that it tends to increase the displacement further in the negative direction. So your particle is going to move further away from the equilibrium position. So even the slightest of the displacement will throw the system completely out of this equilibrium position. In other words, here the equilibrium is an unstable equilibrium. I can illustrate the difference between stable and unstable equilibria with one more example. Take the case of a pendulum of length L and mass m. So here the movement happens in the gravitational field. We know the expression for the gravitational potential energy. So if you take the vertical height as z, then potential energy U is going to be mgz. Okay. Now z I can write in terms of angle theta and length L. So if you see here, z is nothing but the distance from here to here. Okay. Z is the distance from the bottom point to your mass. Okay, so this is z. So we know that this entire length is L, and if this angle is theta, then this distance from this point to this point is L cos theta. So the difference is going to be L minus L cos theta. So z equal to L minus L cos theta. So I can write U equal to mgl 1 minus cos theta. Now let's consider two positions. Theta equal to 0, where the object is going to hang vertically down. Then theta equal to pi, where the mass is going to hang vertically up. And let's see what is the potential energy at these 2 points. Let's first calculate du by dx, because we know that for a position to be equilibrium position, du by dx has to be 0. Okay. So when theta equal to 0, we know that cos 0 equal to 1. So u is going to be 0 there. So du by dx is going to be 0. So theta equal to 0 is 1 equilibrium position. What happens when theta equal to pi? Cos pi is minus 1. So 1 minus minus 1 is 2. So you have 2 mgl. So mgl2 all are constants. So when you take du by dx at theta equal to pi, derivative of a constant is 0. So once again you get du by dx equal to 0. So theta equal to 0 and theta equal to pi. Both are equilibrium points. Now which is stable and which is unstable? So that is determined by the value of the potential energy. So if you plot u as a function of theta, you will find that when theta equal to 0, the value of the potential energy is minimum. On the other hand, when theta equal to pi, the value of the potential energy is maximum. So from our previous experience, we know that when potential energy is minimum, that corresponds to a stable equilibrium. On the other hand, when the potential energy is maximum, that corresponds to an unstable equilibrium. That's why the pendulum is able to hang vertically down for any amount of time, but it is not able to hang vertically up for a long time. For example, if you take the bob all the way up and when you release it, it may stay there for a second or a fraction of a second. After that, it will come down because this position is not an equilibrium position. And when you release, what happens? It's going to oscillate about this theta equal to 0 point for some time. The oscillation slowly dies down. Finally, it settles at theta equal to 0 point. And at that point, it can stay for any amount of time because this is a stable equilibrium point. So in other words, a system is stable at the bottom of a potential energy valley. For example, 0, 2, pi, all these are valley points. Here, the system is stable and the system is unstable at the top of the potential energy hill. So pi is the energy hill, here it is unstable. Now mathematically, how do you identify the stable equilibrium points and unstable equilibrium points? So we know that force is nothing but negative derivative of potential energy minus du by dx, and we know that when du by dx equal to 0, it's an equilibrium position, and if the value of potential energy is minimum, that corresponds to an unstable equilibrium point, and if the value of potential energy is sorry for the typo here, it should have been other way. Let me correct it just a second. Now this is corrected. So maximum U corresponds to unstable equilibrium and minimum potential energy corresponds to stable equilibrium. Now, how do you identify these two mathematically? Okay, for example, if you have a local minimum here. So now from our understanding, we know that this corresponds to a stable equilibrium point. Now, how do you identify this? So we know that at the minimum point, du by dx is going to be 0. Now what you do is you take the second derivative, d square u by dx square. And what's the meaning of second derivative? This will give you the change in the slope, right? Du by dx is the slope and the change in slope is given by d square u by dx square. And you monitor the change in slope. So on the left hand side, the slope is decreasing. You have a negative slope. At this point x0 or the equilibrium position, you have slope being 0, and on the right side you have a positive slope. Slope is increasing. So you start with negative slope, it increases to 0, it further increases to a positive value. In other words, the change in slope is positive. So if you calculate d square u by dx square for this kind of a graph, it is going to be greater than 0. So if the second derivative is greater than 0, then you can conclude that that point is a stable equilibrium point. On the other hand, if you take an energy hill, so once again at this position du by dx equal to 0, now you take the change in slope d square u by dx square. On the left hand side, you can see this is an increasing slope or a positive slope. At x0 you have slope being 0, and on the right side you have a decreasing slope. Slope is negative. So you start with positive slope, it decreases to 0, it further decreases to a negative value. In other words, the change in slope is negative here. So when you calculate d square u by dx square for this kind of a graph, you get this is less than 0. So if the second derivative is greater than 0, that corresponds to a stable equilibrium. If the second derivative is less than 0, that corresponds to unstable equilibrium. You have a third scenario where you have a constant potential energy function. For example, this case. Okay. So when you have a constant potential, du by dx is going to be 0, and the second derivative is also going to be 0. This kind of a situation is known as neutral equilibrium. So this is how you mathematically identify the positions of stable and unstable equilibrium. Now what we have drawn in these graphs are known as energy diagram. Okay, so you plot potential energy or kinetic energy or the total energy as a function of the position of the particle. This is the energy diagram. In classical mechanics, there are two approaches to study motion of a system. Either you can write down the equation of motion by considering all the various forces acting on the system. When you solve the equation of motion, you get trajectory as a function of time. That's one way of analyzing the motion. Alternatively, you can draw the energy diagram of a system, and from that energy diagram, you can infer a lot of important information related to the motion of the system. Okay. So in certain cases, energy diagram approaches are more useful. In some other cases, the Newton's equation method is more handy. So let's try to see how to analyze energy diagrams of certain simple one-dimensional system. Okay. So typically in energy diagram, you draw either the total energy E or potential energy U as a function of position. So once you know the potential energy and total energy, you can calculate kinetic energy from the expression K equal to E minus U, because the total energy or total mechanical energy is sum of kinetic energy and potential energy. And we know that kinetic energy can never be negative. This is half mv square, right? V square is always positive. Mass is always also positive. So kinetic energy is always positive, which means the motion of the system is constrained to the region where u is less than or equal to E. So this is our domain of analysis. Now there are two types of motion. One is known as bounded motion and the second one is known as unbounded motion. Let's first try to understand what is bounded motion using a one-dimensional harmonic oscillator. We now know that for a 1D harmonic oscillator, the energy diagram corresponds to a parabola. So the minima point here is the equilibrium position. Now what happens? You take the case of a simple pendulum. Okay, so when you pull the bob to one side and release it, what happens? You can see that about the equilibrium position, it oscillates under the influence of the restoring force. Okay. Now you can monitor the potential energy and kinetic energy of the system. Now you will see that at the midpoint, at the equilibrium position, the kinetic energy is maximum, or the speed of the bob is maximum. Now when it goes to the right side, what happens? Its velocity keeps decreasing, or kinetic energy keeps decreasing, and finally when it reaches the extreme point, the kinetic energy is minimum. Here velocity is 0. Actually the bob stays there for a fraction of a second still. After that it comes in the opposite direction. Now we know that the total energy is nothing but kinetic energy plus potential energy. So when kinetic energy is decreasing, what happens is the value of the potential energy increases. That is what this parabolic curve represents. Right here, the potential energy is increasing. Finally, at this extreme point, the potential energy is maximum and kinetic energy is 0. Now from this position, what happens? Under the influence of the restoring force, the bob comes back in the opposite direction. So when it moves downwards, the velocity increases. So the kinetic energy is increasing, the potential energy is decreasing. At the equilibrium position, it has the maximum velocity. In other words, it has the maximum kinetic energy. At this position, the potential energy is minimum or zero. Now the bob starts to move in the opposite direction. As it moves up, velocity decreases, kinetic energy decreases, consequently potential energy increases. Finally, at this extreme point, kinetic energy is zero and potential energy is maximum. So at any point in the motion, you will notice that the sum of kinetic energy and potential energy, the total mechanical energy, is a constant. In other words, total mechanical energy is conserved. So this is the implication of motion under a special type of force known as conservative force. Now these 2 points, x1 and x2, are known as turning points. What happens? Because the motion of the bob changes its direction from these 2 points. So x1 and x2 are the turning points. Now from this energy diagram, it is clear that the motion of a harmonic oscillator is a bounded motion. What do I mean by bounded motion? Because if you take the case of a simple pendulum, bob can move only up to this point x2 and x1. Beyond that, it cannot go. In other words, the motion of the system is bounded by these 2 turning points. Right? Because this is the total mechanical energy of the system. At no point in time, a system can have a potential energy or kinetic energy greater than the total energy of the system. So this motion is bounded by this finite value of the total energy. Now you can see that as E increases, the turning points move farther and farther off, but the particle can never move away freely. On the other hand, if you decrease the total energy, the amplitude of the motion is going to decrease until finally, for total energy E equal to 0, the particle lies at rest x equal to 0. So this is a classic example of a bounded motion. So every linear harmonic oscillator executes bounded motion. Now let's see an example of an unbounded motion. So consider the case of a particle constrained to a radial line and acted on by a repulsive inverse square law force given by A by r square r cap, where A is a positive constant. So this is some kind of a repulsive force. Let's calculate the corresponding potential. So potential is nothing but negative integral of the force. So integral of 1 by r square is minus 1 by r. So when you take negative of that, you get u equal to a by r. So potential energy is positive, meaning by convention this is a repulsive potential. Okay. So if you plot potential energy as a function of r, this is what you get. So this is 1 by r function. So obviously when r increases, the potential energy is going to decrease. On the other hand, when r decreases, the potential energy is going to increase. Okay. Now here you can see there is a distance of closest approach r minimum. So the motion is not bounded for large r since u decreases with the distance. On the other hand, for small r, the motion is bounded at r equal to r minimum. In other words, if you try to decrease r, the minimum value you can reach is r minimum. Beyond that, you cannot reduce. In other words, you cannot go all the way to r equal to 0, because after this point, the potential becomes hugely repulsive. So how much ever you try, you cannot move your particle beyond this point. I can illustrate this with an example or an analogy. You assume that at this y-axis you have a very strong magnet, like a magnet with its south pole on this axis. Now you try to bring a small magnet from this direction, a small magnet with its south pole directed towards the left. Okay. So at every position, this magnet is going to experience a huge repulsive force from the strong magnet. But when you are very far from the axis, the repulsive force is very small, right? So when you apply some force, you will be able to move it towards the left. So as you move closer, you will experience more and more repulsive force. Finally, it reaches a point beyond which, how much ever you push, you are not able to bring it closer to the axis. What's the reason? Beyond this point, the repulsive force is very, very huge. With your applied force, you are not able to overcome that. So there is a minimum distance you can reach. In other words, for small r, your motion is bounded. You cannot go beyond this point. On the other hand, you can take this magnet to any distance away from this axis. It doesn't matter. So for large r, the motion is unbounded. So if the particle is shot towards the origin, it gradually loses the kinetic energy. Remember, kinetic energy is the difference between this flat line, the total energy, and this potential energy. This gap is kinetic energy. So if the particle is shot towards the origin, you can see the gap is decreasing, which means the particle gradually loses kinetic energy until it comes momentarily to rest at this position Rmin. So here it experiences a huge repulsive force or repulsive potential. As a result of that, the motion then reverses and the particle moves out towards infinity. So this is an unbounded motion. For small r, this is bounded. For large r, this is unbounded. But the generic example is a combination of bounded and unbounded motion. So this is what you are going to encounter in most of the practical systems. With some potentials, either bounded or unbounded motion can occur depending upon the energy. For example, consider the interaction between two atoms. So this is the potential energy curve corresponding to two interacting atoms. Okay. So here you can see that at large separations, the atoms attract each other weakly with van der Waals force. And van der Waals force is distance dependent. It varies as 1 over r to the power 7. So when the value of r is very, very large, the van der Waals force strength is very, very small. So correspondingly, the potential is also small. So when r equal to infinity, literally your potential is going to be 0. That's why you start from 0 potential. So at very high r, the force is negligible. Consequently, the potential is 0. As the atoms come closer, the electron clouds of the atoms begin to overlap, producing some strong forces. So as a result of that, your potential energy is going to either increase or decrease along the axis. Okay. So if the force is attractive force, then we know that attractive potential is negative. So you have potential energy increasing in the negative direction. Or you can say potential energy is decreasing. Okay. Now, if the force is attractive, the potential energy decreases with decreasing r, and finally at this position, the potential energy is minimum. And from our previous experience, we know that minimum point is the stable equilibrium point. But if you decrease the position or decrease the distance further, at very short distances, the atoms always repel each other strongly, so that the potential energy increases rapidly as r becomes small. So you start at potential energy equal to 0, then you decrease your potential energy, then you reach the equilibrium position where potential energy is minimum. If you try to bring the atoms even closer, then you will see that the potential energy is increasing rapidly. Now let's try to understand what are the various energy regimes in this diagram. Now for positive energy, E greater than 0. So this is the region, E greater than 0. You can see that this is unbounded region. The motion is unbounded and the atoms are free to fly apart. They can occupy any position there. On the other hand, if you consider the regime of negative energy, E less than 0. For example, you imagine that your particle is somewhere here or here. Okay. So this is similar to the case of a one-dimensional classical oscillator, right? Harmonic oscillator. because this is an unbounded motion, right? So the atoms cannot come closer beyond a point RA. Similarly, the atoms cannot move farther apart beyond this point RB. In other words, RA and RB are your turning points. So the motion is bounded by these 2 points. So when energy is less than 0, this is a bounded motion. Now some of you would have guessed that a bound system, like 2 atoms bound together, is nothing but a molecule, right? So our sketch represents a typical diatomic molecule energy diagram. Now I can illustrate this with the example of a hydrogen atom. So you know that hydrogen can exist in atomic state, or 2 hydrogen atoms can combine together and form a hydrogen molecule, H2 molecule. Okay. Let's try to understand the formation of a hydrogen molecule using the energy diagram. First, let's see what are the various forces acting in such a system. So you have 2 hydrogen atoms. So inside the atom you have a heavy nucleus. Inside nucleus you have protons and neutrons. Neutrons are chargeless. Protons are positively charged. Because of that, nucleus is positively charged. Since nucleus is heavy, it doesn't move much. Okay, so you have a heavy positively charged nucleus at the center. Now, around the nucleus you have electrons. Unfortunately, quantum mechanics says that I cannot pinpoint the location of the electron exactly. This is the uncertainty. So I can only say that there are some regions where there is some finite probability of finding an electron. So that's why I represent electron like a cloud. So I have an electron cloud. As you know, electron cloud is negatively charged. Okay. So you have 2 atoms, and with its own nuclei and electron cloud, what are the forces possible here? The nuclei of these 2 atoms, they repel each other, because we know that like charges repel and unlike charges attract. So these 2 repel each other. The electron cloud also they repel each other. So both electron clouds are negatively charged. They also repel each other. But the nuclei of the first atom can attract the electron cloud of the second atom. Similarly, the nuclei of the second atom can attract the electron cloud of the first atom. So you have some repulsive forces and some attractive forces in play here. And when these atoms join together to form a molecule, the distance between the 2 nuclei, that is known as the bond length. Now let's see how does this entire motion or entire dynamics can be understood using the energy diagram. Okay. So you plot the energy diagram. So on the y-axis you have the potential energy. On the x-axis you have the internuclear separation. Now you start with very large separation. For example, R equal to 300 picometer. Pico is 10 to the power minus 12. This is a very small number, but for a system like hydrogen atom, this distance is very large. So 2 hydrogen atoms are very far. We know that at a very large separation, the force acting between the system is the van der Waals force, which varies as 1 over r to the power 7. Since r is very high, the force is negligible. Consequently, the potential energy is almost 0. So you start with very low potential energy. Now when you bring these 2 hydrogen atoms closer, for example r equal to 150, at this position what happens is that the attractive force between the nuclei and the electron cloud, this is the dominant force here. Okay. We know that attractive potential is negative potential. That's why you see when these 2 atoms come closer, the potential energy decreases. Finally, it reaches the minimum point. So at this point, the system reaches its equilibrium position. In other words, a stable hydrogen molecule is formed when the distance between these 2 hydrogen atoms is r equal to 74 picometer. This is the equilibrium distance. Okay. So this is the formation of the hydrogen molecule. So you can see why do we say this as a stable system. If you look at energy, energy is minimum. So we know that whenever energy is minimum, that corresponds to a stable equilibrium position. Now what happens if you try to bring the hydrogen atoms even closer? Now what happens is from this point onwards, the repulsive forces between the two nuclei as well as the two electron cloud, this starts to grow in strength. And repulsive potential is a positive potential. Okay. So previously, because of attraction, you have a decreasing potential. Now this is going to get compensated by the increasing potential due to the repulsive force. So when you bring atoms closer and closer further, the repulsive potential gains in more and more strength. As a result, the potential energy is going to increase. Finally, at this position, attractive potential is completely compensated by the repulsive potential. You have the net potential being 0. And if you try to decrease the distance further, you have a totally positive potential energy due to the dominant repulsive interaction. Okay. So this is how you understand the interaction of two atoms using the energy diagram. So once again, when the separation distance is large, you have effectively 0 potential. Then for moderate distances, the potential is negative due to the attractive interactions, and beyond the equilibrium position, the interaction is always going to be repulsive. Consequently, the potential energy increases. You can also understand atomic collisions using this kind of an energy graph. So we know that for two atoms to combine and form a molecule, the energy has to be less than 0, or energy has to be less. So if they have very high energy, the motion is going to be unbounded, right? So here they will not form a tight system. So if two atoms collide with positive energy, they cannot form a molecule unless some means is available for losing enough energy to make the total energy negative. In general, a third body is necessary to carry off the excess energy. Sometimes the third body is a surface, which is the reason surface catalysts are used to speed certain reactions. For example, if you take the case of hydrogen in atomic form is quite stable. But when you take a piece of platinum and keep it inside hydrogen gas, you will find that the stable atoms join together to form hydrogen molecule. So here what happens is, hydrogen atoms have some affinity towards the platinum surface. So they come and attach on the surface. Now, when two of the hydrogen atoms on the surface of platinum, when they collide each other, what happens is the excess energy they releases. And the platinum surface absorbs this excess energy. So previously, two atoms were in a state E greater than 0, very high energy. Now they lose some energy, which means now they are in a state E less than 0. So this is the bounded state. In other words, they form a tightly bound molecular system. So they form a hydrogen molecule. Now, unlike hydrogen atom, hydrogen molecule doesn't have an affinity towards the platinum surface. So what happens? The molecule leaves the surface. So when the collision between two hydrogen atoms happen, the excess energy is absorbed by the platinum surface. That's why if you observe carefully, you will see that the platinum surface is glowing because of this excess energy. So this is one way catalysts work in some reactions. Now, presence of a surface is not mandatory. You can have a catalyst atom or molecule. So here what happens? Two hydrogen atoms will collide. They release the excess energy. And if the catalyst atom or molecule is sufficiently close to these two hydrogen atoms, it can absorb that excess energy. So the hydrogen system is losing energy. As a result, it forms a stable, tightly bound molecular system. Now, for this to happen, the catalyst molecule should be very close to the hydrogen atom. This is achieved by compressing your system or applying very high pressure. Okay. So this is how you can get some of the useful information regarding the motion in an atomic system using the energy diagram method. So that's for today. Thank you.